Thank you, folks, for having me back here again. Um, okay. So let me jump straight into the talk, what I'm going to do. This talk, for a change, is not a hand-wavy talk that I'm now subject to be doing. You know what they say about aging security researchers, like you move from research to hand-wavy talks to keynotes, and then you go into oblivion. Like one fine day, you're done. I think I tried to buy some time back with this talk. So this talk essentially is basically 4 years plus of me fiddling around with what started out as clumsy little scripts, very ugly, until it kind of became usable, not only by me, but by my students. And then I decided, okay, we can't keep a thing bottled up, so why don't we open it up? And this brings me to why we're here. I'm going to give you an overview of two things. Something that Joe Fitz hates very much, emulating firmware. He doesn't like it. So I thought, okay, well, let me try it. So we're going to talk about what it takes to emulate firmware on an IoT device. And then I'm going to give you a tour of ARMX and officially release it right here. So, well, my name is Saumil Shah. I've been doing this stuff since a very long time. In fact, this photo, no, this is not at the Okura, but it so happens that every time there's a hack in the box, there's also President Putin wandering around. This is not the first time. So anyways. Okay, so let's get to what ARMX is and what are the motivations of doing ARMX. At some point, I started teaching exploit development, which was many years ago, on the x86 platform. Then I got a little tired of it after doing it for a long time. So I decided, well, let me learn ARM exploitation. And I started teaching ARM exploitation. And Mark Rogers was one of those who suffered me in the very second class that I actually taught, which was actually extreme disaster. But somehow he's still friends with me. Whenever you want to teach students, you've got to build something that works reliably and stuff that you can afford breaking and then reassembling very quickly. We can't do that with actual devices, and sometimes devices are not available in the quantity. So if I want to teach how to break routers, how to break IP cameras, well, the first thing I like to do is emulate them, create a software model of it, and if we can break it in software, in an ideal world, we should be able to take that exploit and straight away attack the hardware. We've been doing this in virtual machines for a very, very long time on the x86. You create a Windows VM, you create a Linux VM, you exploit it, it works, everything's great. Things are a little more complicated in the IoT world. It's not as simple as, okay, you grab a file, you create a right-click VMware player, launch it, boom, off it goes. It doesn't happen that way. So this led me to a deep dive journey into embedded devices from noob to not a noob. I started looking at it from the software level going down. And as I built it up, I started playing with QEMU and a few scripts. It started taking shape, and now we have ARMX. So essentially, this is an ARM firmware emulation framework. I've got it working for a few versions of the ARM CPU, all 32-bit. It uses QEMU as the main workhorse, but then there's a lot of niceties on it. My ultimate goal was basically, can we get as close to an IoT VM as far as possible? Like, can I boot up a router in an emulated environment? Can I boot up an IP camera in an emulated environment? Not only that, can I then fuzz it, debug it, reverse it, exploit it, and take my findings and apply them directly to a real-world device that we can find? So essentially a virtual device for research purposes, and this is the goal of ARMX. While doing so, I actually gained a lot of insight into the world of both emulation and actual device, like how things work. things like cache coherency, things like SPI memory, things like little issues with firmware, with devices, with kernels. Whole deep dive into the tunnels and the warrens of build root, which is quite confusing, and eventually got things to work. So this is typically what ARMX looks like. Yes, there's going to be demos, and you click it on, you get a nice little menu. Every device that you emulate is like a text-based VMware player for IoT devices. You can add your own device, you can create a template, drop some firmware in, drop some key value pairs in, cobble together a few scripts, spend a couple of weeks tweaking it, and then you get it reliable, you just add it, and it should kick off and go. So I'm going to demo all this stuff. First, let me walk you through the architecture and the background of IoT devices. So if you take a look at any IoT device, essentially it's nothing but a special computer, which has its own CPU, has its own peripherals, runs a kernel, has a file system launches its processes, and you have your applications on top of it. So eventually when the whole thing boots up, it offers you functionality, you get a UI, you get some client-server processes or whatever the device is supposed to do. Internally, there's a lot of things going on. And if we want to emulate this, we need to go down all the way to the very deep details of how everything works. Devices are very unlike disk-based computers. Today we take a computer, it has a large disk and it has persistent storage, fast storage, lots of memory. Nothing like this happens in the IoT world. You have small memory, you have limited memory, you've got flash memory, which is not as writable as you wish it to be. You can flash it and read as many times as you want from it. Persistence is achieved by a few tricks. One of them being non-volatile RAM. You store just the right values that you need in the non-volatile RAM. And the entire system is built to basically boot off from nothing. Everything lives in the RAM disks. So when you power on your Linksys router, the lights blink and they keep blinking for quite a few, almost like a minute or so until the whole thing comes up live. And there's a lot of background work that's going on. I'll explain you the process of how devices start up, and then we'll talk about how what it takes to emulate each one of these. I'll give you a tour of the components, and hopefully the demos work. So if we consider the boot up process of any device, you start with the hardware, the system on chip. Along with the SoC, you have flash memory, and there's firmware that is living on the flash memory. It's been flashed by the manufacturer, or you can flash it during an update process yourself. The flash memory is typically called, is an MTD device, memory technology device, which contains three things. At a bare minimum, it contains the bootloader, it contains a kernel, and a compressed file system that it's going to use. And parts of the MTD also are mapped to NVRAM, that is non-volatile RAM, which stores the essential configuration details for the device. So this is basically the device in power off mode. When you power it on, the control kicks in, the CPU passes the control to the bootloader. The bootloader loads either it's like, say, Broadcom's common firmware environment or D-Link's loader or whatever you may have, or U-boot or a derivative thereof. The bootloader will then look at what partitions exist, what MTD blocks exist, and then it'll go and find the kernel. It's configured. The kernel kicks off. The kernel will do a further scan on the MTD blocks, find out where the root file system lives. It will then uncompress the root file system into RAM disk. Nothing is persistent on a device. Everything happens on a RAM disk. So you get it uncompressed into RAM disk. Once the thing is uncompressed, the kernel passes control to the init scripts, the user land. Now, the init scripts for every device are are a maze. They're like spaghetti code, like you won't believe. It's got clumsy scripts and errors and everything together. The first script will look for other scripts to start up, and each script will look for its application and components. And what happens is, because there's no configuration persisting to begin with, these init scripts will then build up all the config files on the fly. Everything from etc password to the web server configuration to Samba configuration to wireless SSIDs, all that stuff is then loaded from the NVRAM using a userland library called libnvram most typically, which makes call to the NVRAM device using IOCTL, loads all the config up, creates the config files on the fly with the parameters that are saved in NVRAM. And once the config files are up, it starts invoking your various services like Samba, DNS mask, FTP, HTTP, whatever it's built with. And once the default services boot up, then your custom applications boot up on top of it, your admin interface or your streaming video or your wireless routing or DNS management or whatever the device is programmed to do. And at this point, the device is ready. One of the challenges in emulating this was to figure out basically how to deal with all the stuff in purple. All this stuff. Figuring this out individually took a lot of time. But what I ended up doing was something like this. More or less, we want to leave the userland part unchanged, as is, not modify it beyond what is necessary. Instead of the CPU, we are going to take a QEMU environment, choose a machine type which closely resembles the device that is being emulated. Now, I haven't gotten to a point of expertise where I can actually emulate the exact hardware. I mean, there are QEMU wizards who can do this. I'm not one of them. So I would take a default prototype board which most closely matches it. Especially, I want to be very particular about the CPU type. That is something I really want to match. So is it an ARMv5, ARMv6, ARMv7? Choose the correct CPU type, choose a proto board that supports it, and as many peripherals as you can manage. Now, if you're talking about, say, a Wi-Fi router, then I don't have real Wi-Fi that is emulated yet. I know Ralph Phillip and a few others have done that. They've actually emulated the Broadcom hardware for the Wi-Fi, but I have not reached that level yet. Or if you're emulating an IP camera, then you need a frame buffer device to grab video images from. I still don't have that. It's just a matter of creating a new device definition and having a proper driver for it, most likely something like Video for Linux. But that's still like in the near future on my to-do list. The NVRAM emulation is also a challenge. I was struggling with this until like middle of this year when I finally figured out how to do a semi-emulated NVRAM environment. I still don't have it mapped to an MTD block, but I have it mapped to shared memory, where you can pre-populate the NVRAM with configuration, and the emulator will use NVRAM like it is from a real device. I mean, this added a lot of flexibility to emulation. And then some of these config scripts, you might have to hand patch yourself. Because every device, when you take the default firmware, it is configured with default factory settings, like a default IP address or a default password or whatever. Now, by itself, it will run just fine. But let's say you wanted to participate on the network properly, then you may have to go and hand edit the IP address in some config scripts here and there. Once you do that, I mean, this process of R&D takes about a week for every new device that you want to play with. But once you've gone through that whole R&D process, the modifications are stable enough. And then what you can simply do is power on the QEMU. It will go and load the kernel. And the kernel will then go and work through the init scripts and hopefully get you the full thing booted up. So what you need to start with is you need to start with contents of the NVRAM. You have to get it somehow, and I'll explain how you can get it. You need to grab a kernel which most closely matches the kernel on the target device. Now remember, you can't do this without first playing with a physical device. You need the physical device to play with. You need to probe it somehow, figure out what the contents are, and then you can start emulating. You can't like just do it blind. Once you got a closely matching kernel, and I use buildroot to build all the custom kernels for this stuff, which not only match the CPU or the version number, but also, as far as possible, the kernel config settings. Now, some kernel configs are really, really crazy. Sometimes you may get lucky. You may get procconfig.gz and get a copy of the kernel settings from the device. Has happened. Or sometimes you're not that lucky. You have to guess what the config settings are, and that itself is a lot of work. Once the kernel is built, then you fix the config scripts. You have some drivers which will load, some drivers which won't load, unfortunately, because of missing devices. And then you create a chroot environment around the root file system. It's like, again, I know it's too complex. I'm going to show you this thing in a demo. I want to give you a roadmap of what's coming. And if everything goes right, the boot up process will go through with a few errors, but in the end, you will get stuff working, sometimes completely, sometimes partially. Like here, if you want to get the IP camera view on your iPhone, you can't because there's no video device. So it'll show you like gray squares instead of where the video is going to come. But you can still play with this virtual IP camera just as you would on a real device. You can do all the bug hunting you want, except for the video drivers. You can play with the admin interface. You can do web hacking. You can scan for backdoors. You can do dynamic tracing. You can do reverse engineering. You can fuzz this thing and get crashes on it. You can do exploit development on this camera itself and literally take the exploit as is and target it on a real IP camera. If all the emulation is correct, then it should work with zero modifications. And that was the goal that I set out with. So now let me show you the startup process. We initially start with the QEMU and the limited hardware and a custom kernel. And then in RMX, you get to define a machine. You just create a CSV file, drop some configs in it, and it gives you a new line. When you click it, it boots up into the default kernel. At this point, it's like as if the device has started up and the kernel is loaded. Once your kernel is loaded, you then want to go and uncompress the file system and start playing with the init, start invoking the init scripts. Now, instead of uncompressing the file system dynamically, what I do is I just uncompress it manually and drop the file system in as is. This has two advantages. One is you don't have to play with uncompression on the fly. And second is you get a persistent file system to modify. You can then drop your own tools in it if you want to. You can read write to it externally as well. And it stays just like a regular disk file system. So then you say, OK, after the kernel is booted up, you get this type of a menu saying you either want to direct shell into the environment, or you want to now go ahead and kick off the user land side of the device. And when you kick off the user land side, you first get a user land shell. Here's a screenshot showing you this is the processor type that I'm emulating. This matches the one that is on the IP camera, and the kernel version closest to the one on the IP camera. Unfortunately, the one on the IP camera kernel version was way older than this, and buildroot simply would just not build the kernel, just crash out with GCC errors, and I could not play with the make files then. Once this is done, then you look for the first init script and kick it off, and then a chain reaction will start. The first init script will kick off the second init script, and the second will kick off the third, until you start getting to a point where all your services are essentially loaded and running. Sometimes you might give an error, like this one showing that you can't open up video codec because there's no video hardware in there. That's okay. Sometimes errors don't affect the rest of the components. And once things boot up, you actually get a very workable version of the device. So let's start seeing how, let's start taking a look at our mix. This is where the demos have to work. Okay, so here's our mix. I'm going to give you a quick tour of our mix. There's a lot of confusing stuff in there, so I'm not going to go into all those details. I'm going to do a proper documentation on the website for you to follow. This is basically a regular Linux VM, and there's a folder here called rmix, which essentially contains it contains all the definition, it contains all the loaded firmware. I've been playing with this in my work environment. I use this for actually pen testing customer devices. I've been using this in my classes. Students have found 4 days using this approach. Like one of my students found a 0 day in the Netgear R6250. Another one found the IP camera that I'm going to demo. There's one on the Cisco, which somebody else found, not my student. But and then a couple of 0 days are still unreported. And Jan brought over an IP phone from Germany, so that's the next one that I'm going to emulate. And I know there's a bug in it as well. So here's all the devices that I've implemented. Let me give you a basic tour. The first file which governs everything is a devices file. Now everything is super ugly because I'm a command line guy. The only programming languages I know are C and shell script. Yes, I don't know Python, I admit it. I will never suffer Node.js or anything like it. Exterminate all that if I can get a chance. No JSON, no XML shit for me, nothing of that. Good old CSV files, comma separated variables. Every row contains a device definition. If you don't have something, comma, 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 until you have something, right? So here's a classic definition. Let me show you. This is the RV130. This is a Cisco router that I emulated. The first one is just the device ID. Then here you see which QEMU board you want to use. This is a RealView emulation board. The CPU is ARM11 MP core. There's no DTB file. Uses 128 megs of RAM. This is the kernel, the ZImage 263114, compiled specifically for RealView, and RealView does not support thumb binaries, so I disabled that from the kernel. This kernel thing took a while. And then here you have some file system, like what is the emulated SD card, and these commands, eventually these commands are the default for the kernel to start with. So your root device is in MMC block 0 and so on. Let me give you a tour of the actual device. So now if you go into this RV directory, you always have these files. You'll have a config file which contains further definitions about the device. So let's say you want to emulate one, you'll create a template, you'll create a config file. The config file tells you where the ini file is, where the root file system is. Do you want to enable ASLR, yes or no? Actually, on the Cisco router, there is no ASLR enabled. But if you want to play with it, you can do that. And this is the init scripts to fire off. I'll show you the ini file, the NVRAM file. These are the settings that are persisted in the NVRAM of the Cisco router. You can grab them using 2 or 3 different techniques. But these are all the config settings that it needs, including passwords, IP addresses, and such. Now, some of the things you may need to fix here would be stuff like this. This IP address is not the default one, but I have modified it because I need to make it work with the IP address of my VMs. So like a couple of modifications like this is what you need. And then let me show the kernel. So here's the kernel. This is compiled from build root. That's its own process of defining the kernel and compiling it. The root file system, this is basically the extracted compressed file system from the Cisco router. You grab it, you uncompress it, and this is basically all the files, devices, and the entire thing that comes from the firmware is dropped into this rootfs. You need this part as well. And then lastly, there's a script called run init, which does a few things like creates a started thing, It parses the config file, preloads the NVRAM into the shared memory, and then it invokes the chroot and starts off all the init scripts of the router. So I'm hoping it works, yeah? Let's give it a shot. So I'm going to click this on. Oh. I'm going to enlarge the fonts so we can read. Very good. So here we are. We load the Cisco Wi-Fi router. Click it. The kernel boots up. This is kernel 2.6.31 compiled with build root. Although it gives you a login prompt, I'm going to leave this console alone. And then we will see what happens when if I log in, I can log in from here, or I'm going to create a separate login window, which basically, here it is. Yeah, so with the login window, I can say, okay, so let's start the router. Now, when you click start, what you're seeing on the screen is all the NVRAM being populated in the shared memory, lifted from the ini file. And eventually, it get to a point where you can say, okay, it's going to start the userland processes. Here we go. Press enter to start. And when I hit start, you can see all sorts of error messages start appearing on the console. This is actually quite normal. Some error messages are genuine. Even they also happen on the actual console of the Cisco router. And some error messages happen because I don't have some devices, like I don't have Wi-Fi, or it's trying to look for the Wi-Fi hardware. It doesn't find it. Like you can see, no device present at something. But it still eventually goes through. And if I open up another terminal to look into what's happened. So this is a shell in the environment. If I now look at the processes that are running, right, you can see a whole lot of processes got invoked. So here's a pre-init process, and there's rogue AP detect, CPU use, HTTPD, network attached storage, WWAN, wireless WAN management, WAN info, its own SSH daemon, and whatnot. So all this stuff got started up. And if I now open up a browser and try and open the IP address, you can even see that it's pulling out the values dynamically, or trying to. You actually get a login prompt on a Cisco device that doesn't physically exist. And when you log in, here you have a fully virtually functional Cisco router. You can go in and play with all these settings. You can now use Burp Suite to hack the hell out of this. You can now use Frida or whatever you want. You can use a fuzzer. You can grab the scripts, instrument the heck out of it, and it'll produce genuine crashes. You can GDB this. You can do all sorts of fun stuff with it. And this is a great tool for anyone to start learning about IoT devices, IoT hacking, IoT security, and whatnot. So this is in a nutshell ARMX. I'm going to go now into some details. We'll also do a demo where we will emulate an IP camera on the fly. It's going to little be like a cooking show where all the ingredients are cut and prepared and the kitchen stays clean. And then it works, hopefully, on stage. But when you do it, you're going to make a mess in the kitchen. Don't be scared about it. It's going to take some time. It's not that slick and easy as it looks like. But in the end, it does work. And when it works, it feels brilliant. OK, so let me shut this one down. And then we'll get ready for emulating the IP camera. OK. So now we're going to talk about what it takes to emulate a new device. The first thing is you need to know what type of CPU and kernel it uses. Find that out by booting the device, getting some documentation, and somehow figure it out. The next and the most critical thing is to actually obtain a copy of the firmware. And this is, well, not very difficult, but not that easy either. There's 3 ways of getting firmware. And by firmware, what do we really want? We want root file system and the NVRAM, preferably. The best way of doing it is by actually lifting it straight from the chip. If you're Joe Fitz, you can do that in your sleep. For other guys like me, we need like a $300 A640 device and a clip and a steady hand and some luck to suck it out, if that works. Failing this sucking from the chip, you then turn yourself towards the serial console. Open up the device if you have a UART, solder in the ports, get a serial console, and hopefully there's a root shell or some way you can get dropped into root shell, lift it from the root shell. And if you don't have all of that, then you just go to the manufacturer's website or the CD-ROM, then buy a computer which has a CD-ROM, or a CD-ROM drive which you can plug into the computer, and then grab the bin file from the CD-ROM. So this is the lowest common denominator. Here's the firmware for the IP cam on its official manufacturer's site. This is step number 1. We can do better. Step number 2 is you can open up the IP cam. Here you can like probe with a poor man's logic analyzer, which is a multimeter, and figure out where the voltage, ground, transmit, receive ports are. Once you do that and you don't burn the device, you connect it using a USB to serial adapter. And if it all works, you actually get the console on the screen when the device boots up, and you get dropped into a shell. So all the devices that I buy, I then modify them and attach serial ports to the casing and using a hot glue gun and everything. Once you get a serial console, you get a root shell, then extracting the firmware is rather easy. You look at all the MTD devices that are present on there, see which ones have the interesting stuff. Like in this case, there's NVRAM is in MTD5 and root FS is in MTD8. Sometimes the partitions are labeled, which makes it easy. Sometimes you have to guess. You look at proc partitions to find out what the actual device is. And then you just do a DD command, input from the block device and output it over netcat or output it on an SD card that you can plug in or a pen drive you can plug in. Somehow exfiltrate all the blocks out. So this is second way of firmware extraction. You can also get a copy of the NVRAM in this way. And the third way is you take it directly from the chip. And this is an E640, which is clipped on to the SPI flash of the IP cam and literally like lifts it in seconds from this thing. Sometimes it works, sometimes you have to like do some pull-up resistors and such. My dad is the electronics expert, so he always helps me out here. But somehow you then make this work. So once you have the firmware, then let's do the demos. I think we have some time to do the demos. I have basically the bin file from the extracted IP camera using the A64. I have the bin file on my system. We're going to emulate it from bin file to a working IP cam. If the demo gods are with me, that is. So here we go. First things first, let's find out where our stuff is. So my stuff is, here we are. This is the bin file I have from the Trivision 227. The bin file is 8 megs or something. Yeah, it's 8 megs long. The flash device was 8 megs. And usually the best tool you want to use for this purpose is bin walk. So I'm going to bin walk this and extract from here. So it's grabbed some stuff. It found a CramFS file system. And now it's created a new directory, which you can see over here, the extracted directory. And in this extracted directory, you have some config files. It doesn't use NVRAM, but it uses something called sys.conf. So here's sys.conf from the configs. And this will tell you how the configuration goes, like what are the devices, what are the channels, some screen definitions. Here are some DNS servers and MAC addresses. This is the IP address. So things like this are defined in the config. Once you get the file system, you'll have to play with this for a week or so. You have to study it in and out, what's in there. What we really want is this one, the CramFS root. If you look at the CramFS root, this contains the extracted file system, uncompressed file system contents from the IP camera's MTD block. And I'm going to copy, I'm going to move this CramFS root to ARMX in the camera definition right here. So let's say we grab this, we put this there. Let's now go to the camera definition. We will ignore this root fs. It's the pre-extracted root fs. We will use this one that we did just now, CramFS root. So I'm going to modify the config file. Say my new root fs is CramFS root, if I can spell properly. And no ASLR. These init commands I found by playing around with the device, like it ideally has a frame buffer device, which is the ABS628, the ANBash 628 device. I don't have it, so I just touch and create a fake device file. It seems to allow the other scripts to run. And then this is the this is the first script that runs, and this is the second script that runs. How do you find out which are these scripts? Well, when you do the first serial console, you see this stuff booted up. You see it from the console messages. You can figure out what boots first and so on. And then in the end, I just want to get dropped into a shell. So these are the init commands. Now, I need to make some changes. So if I go to CramFS root, what I need to do is change the IP addresses. I go to etc default. And here is sys.conf. I'm going to play with this. I mean, sometimes like you can even do other stuff that the device allows. For example, this device has a Boolean flag for the watchdog timer. And if you're doing R&D with it, you want to disable the watchdog so it doesn't keep rebooting. You just go and turn off the watchdog for these things. Just set them off as disabled and makes life easier for you. Here we go. Where's that IP address thing gone? Come on. There. So I'm going to say boot protocol is static, IP address is 100.2. So my default IP addresses in here are 100.1 and 100.2. This is a gateway. Once I fix this, the config setting is done. This is what we have to fix manually in the config files. And then we have to create the device definition. This last line that is commented out, I'm going to uncomment it. So this is going to add a new entry to ARMX with any luck. Okay, let's see if this works. Okay, click the launcher. Oh yay, the IP camera is listed on there now. Click it on. The kernel gets booted. Yes, great. Thank you. Let's get dropped into the first shell. I'm going to start the IP camera. There's no NVRAM, so we just say click to start. Some errors. Keeps going through. You get BusyBox, some more errors. Here, the web server is started. This is what, and some of these won't open. The encoder and the frame buffer devices don't open. But if I look now, here I have a shell on the console If I do a cat proc CPU info, it is running the same hardware as the actual IP camera is. If I enumerate the processes, you can see that all this stuff, the NV control, the iNet DTCP, HTTP client, task manager, all these are built-in processes of the IP camera. And here's a web server. So first, let's do a test if the web server works. And there we go. IP camera web server is open. Admin, of course. And when you log in, now you don't see, this is the broken image. You don't see the image. I haven't hooked it up to my webcam yet. That stuff is missing. But if you go to like settings and you want to play around with the network settings, the TCP IP setup or the storage settings, you can play around with all this. And it's for all practical purposes, it's a fully functional IoT device. What can we do with it? We can actually now, let's say you want to do some more stuff with it. Let's see, there's some time remaining. Let me open up a shell. This is a userland shell on the ARMX environment. This is not inside the device, not in the chroot environment. This is outside it. But here I can actually use a lot of tools. I can now use a lot of tools. I can use strace to trace what the device is, what the binaries are doing, ltrace. I can check the process memory layout. And I have made sure that the proc file system is shared with these. If I want to inspect the mem space of this PID, cat proc 572 maps. This is the virtual memory layout of the web server. This actually matches exactly with what you find on the IP camera. So now if I want to develop an exploit for this, if I develop an exploit on this one, it's going to automatically work on the IP cam. And this is actually what I use for all exploit development. So if I want to now trace what happens here, let's say we want to put a GDB on this. I have all these tools loaded in the outer environment of ARMX. I have strace, ltrace, GDB server, a few other tools, like all your bin utils are on there. I'm going to load this, double attach GDB server to it. It's listening on this port. And now I'm going to attach, use a multi-architecture GDB on x86 and connect it to the remote target. And by using a multi-architecture GDB on my own native host, I get the luxury of, okay, yes, AdBlock, thank you very much. You're doing a good job. I get the luxury of installing all sorts of GDB init scripts, GDB Python plugins, and make my GDB usable again. I have to do a few other things like give it the proper path so that GDB knows where to load the binary symbols from. And with this stuff, basically you can attach to the remote GDB. The remote host is attached. All your, it is waiting at, I think it's waiting in access or something. It's like waiting at a syscall. If I now look at the VM map over here, it's attached to the right process, user bin webs. I can now continue. And the web server will be running. Let's try and crash it and see what happens here. So, sure, just let's say you're fuzzing it or you're playing with it or you're trying to develop some bugs. Here's a proof of concept crash that actually came from burp fuzzer. You have a very large HTTP request, which is going to blow the web server up. Now, testing this becomes dead easy. Testing this with a debugger on the actual hardware is very, very difficult for a guy like me. Testing it on this instrumented thing, a virtualized environment with real GDB server dropped in, straight away. So here we go. We run the attack. We actually get a crash. And you control the program counter register with AAA something. And what you have at hand is a perfectly functional stack overflow. And not only that, you can actually write a full exploit for this. The web server stopped, so I'm going to go and run the web server again. Because there's no more webs running, the process dies. I'm going to run it again. And this time we will attack it. Here's my final exploit with shellcode to invoke telnet on the remote device. So once I run this, a telnet will be started. There's actually no telnet running here. And after the exploit, a telnet will be launched, which will then give me a shell straight into the IP camera. Here we go. It's given you an error, but if now you do this, here's telnet D that is just freshly launched from the exploit. And you connect on telnet, you get a shell straight away. So you can use this for all sorts of purposes, for testing, fuzzing, web hacking, binary exploitation, reversing, whatever you want to imagine will now be possible. The overall architecture of ARMX, it's basically using QEMU. I'm using NFS to share the ARMX directories between the QEMU and the host system as well. So good old NFS, I haven't monkeyed with it ever since my son Solaris days, but it came in very handy to create the concept of a shared folder from host to guest. And then a whole bunch of scripts and a few little tools, custom kernels. All this is going to be released. I had hoped to get the website up tonight. Last night, I couldn't. So watch this space, armx.exploitlab.net. Watch for an announcement from me. And I'm not just saying this, I'm saying it with a timeline. Before or on 23rd of October 2019, you will have this out there. So with that, this brings me to the end of my talk and my demo. The floor is yours for any questions, comments, anything that you may wish. You may ask me questions straight away, or if you prefer to use Slido, you may ask in the box. Joe.
Can you do any MIPS platforms? Is it just a matter of QEMU swapping out for the MIPS QEMU, or is there a lot more dependencies to ARM stuff?
So next on the roadmap is MIPS. Basically anything that QEMU system something can do, this thing can do it. So ARM is something I've been working on for a while and I'm familiar with it. MIPS is on the roadmap. I'm already working with one POC on MIPS, and I can't see why it can't be extended to a PowerPC platform or whatever. Whatever QEMU can run, we can use this.
And are you using GDB running inside the environment, or are you using the GDB built into the QEMU?
Question about GDB. No, the GDB is not the QEMU built-in GDB. So there's two environments to ARMX. When you boot the kernel, you just can't boot the kernel by itself. You have to boot it with an existing root file system. So this is, the kernel is built with build root. The root file system is also built with build root. And GDB, I've basically built GDB along with build root. So that's the GDB from build root. When you invoke the init scripts, they run in a chroot jail. So the GDB from build root is debugging everything in the chroot jail. And when you download it, and when I make it public and you download it, you'll see the mount commands to basically remount the proc file system, sys file system, and the dev tree across from the chroot to, or rather from the build root to the chroot. So the chroot and build root share the same procfs and dev tree, which makes debugging straightforward on those. Yeah. And you can drop in anything you want on that. It's not limited to just the GDB. Other questions?
How would you deal with encrypted firmwares?
How do we deal with encrypted firmware? Brilliant question. And with all brilliant questions, the answers are not so brilliant. You have to decrypt the damn thing yourself. So if you have the bootloader that will decrypt it and you can somehow pass control to the bootloader, great. If you can't, then you have to like reverse something of it, decrypt it. Typically, unless like the firmware is signed in a trusted enclave, most of the encryption is an XOR key, which is hard-coded somewhere in the kernel or bootloader. You find it, you decrypt the damn thing yourself, and off it goes. If it's like a secure boot with a trusted enclave and things like this, then you got to talk to Cristoforo Mune. He's here. Or you got to talk to somebody who hacks iPhones and stuff like this. Not me, because I don't know how to do that.
Thank you.
One day I'll learn, but that day isn't now. Any other questions? Slido stuff. I want to give a big shout out first to Dr. Quinn, who's sitting right here, Dr. Quinn and X-Swings. They are working on a very different approach to instrumented emulation using their new framework called Chilling, which they've also released. And the stuff they've been doing is quite different, a lot brilliant. Then this, you can dynamically instrument any binary using Python code, like even alter its execution at runtime, and they cover a lot more platforms than our mix. But definitely worth taking a look at their framework as well. And they've already released it. Right. Any other questions? Not.
No more
thank
questions?
you very much for your time. Thank you very much for your time and attention, and enjoy this mega cybersecurity festival. Thank you.